Hi and welcome to Chemipedia chemistry classes for 11th and 12th standard. So this is NEET series atomic structure part 2 previous year questions. Look at question number 17. You are given a formula to calculate energy of an electron in the nth cell. Then four options are given just below that. Among that, one is incorrect about this formula. Right. So look at first option. This is used to calculate change in energy when electron changes orbit. So using this formula, substituting different values in the place of n, you are able to calculate the energy of electron in different cells. By taking difference between them, we are able to calculate change in energy. So option A is the right one. Okay, right. Option B, for electron in the first cell has more negative energy than the electron in the sixth cell, which means that electron which is in the first cell is more loosely bound. It's given that the electron which is present in the first cell is most loosely bound compared with electron in the sixth cell, isn't it? So this is a wrong statement. This is an incorrect statement because the electron in the first cell is close to the nucleus, so it will be tightly bound with the nucleus. So this is the wrong statement. So this is the correct answer actually. Okay, option C is the right one. Look at other two also. Let us check. Option C, negative sign in the energy of electron indicates electron bound to the nucleus has lower energy than electron which is at infinite distance. So that's the correct one. So when you go away from nucleus, the energy of electron generally increases, isn't it? Right. Then the option D, larger the n value, larger the radius of orbit. So when the principal quantum number value increases, the radius of the orbit also increases. So option D also right one. So that the incorrect statement regarding this energy formula is option B. Okay, right. Now we go for the next question. Question number 18. Here you are given some data. Planck's constant 6.63 into 10 power minus 34 joule second. You are given speed of light 3 into 10 power 17 nanometer per second, and frequency also given, frequency equal to 6 into 10 power 15 per second. So what is the lambda value? Okay, so they are asking the wavelength of the light, okay, from the given data. Okay, so let us see how to do this. Now for this we are supposed to use the formula nu equal to c by lambda. I think you know the relation between frequency, velocity and wavelength of light, isn't it? Right. So you are supposed to calculate wavelength, so therefore lambda equal to c by nu, isn't it? C and nu values are given. C is 3 into 10 power 17 nanometer per second divided by frequency 6 into 10 power 15 per second, isn't it? So I cancel 10 power 15 and 10 power 17, so I get 10 power 2, 3 and 6 getting cancelled, so 1 by 2, so 1 by 2 into 10 power 2, which is nothing but 15 nanometer. Okay, therefore the wavelength of the light for the given data is about 50 nanometer. Okay, so look at the options. 50 nanometer, so option A is the right one. Okay, right. Now we go for question number 19. The orbital angular momentum of p electron. So what will be the orbital angular momentum for p electron? So for this we have to use orbital angular momentum formula. Okay, orbital angular momentum formula is square root of L into L plus 1 into h divided by 2 pi. Okay, you are asked to find out orbital angular momentum for p electron. So for p electron, azimuthal quantum number value L value is 1, isn't it? Right. Now I substitute that value in the formula, so I am getting square root of 1 into 1 plus 1 into h divided by 2 pi, isn't it? So square root 2 h divided by 2 pi, isn't it? Now the denominator 2 I write it as twice square root 2, isn't it? So one square root in the numerator and denominator gets cancelled. So finally I am getting h divided by square root 2 into pi, h divided by root 2 into pi. That is the orbital angular momentum for p electron. Okay, now let us look at the options. Look at option A, h divided by square root 2 into pi. So that is the right answer. Okay, Question number 20. Maximum number of electrons in the orbital with n value 4, L value 3. So you have to find out how many maximum number of electrons can be located in that orbital with n4, fourth cell, L3, isn't it? So subcell is nothing but F subcell, 4F subcell. So you have to calculate the maximum number of electron in the 4F subcell, isn't it? Right. So you know that F subcell can have maximum of electron about 14, isn't it? So the answer is nothing but 14. So look at the options given. The maximum number of electron present in the 4F subcell is about 14. Question number 21. 4 quantum numbers for the valence electron of rubidium. So you are asked to find out the 4 different quantum numbers for the valence electron of an element rubidium whose atomic number is 37. Okay, right. You know very well that rubidium belongs to first group, isn't it? So it belongs to alkali metals, isn't it? So hydrogen, lithium, sodium, potassium, rubidium. So that rubidium comes under period number 5. So it is located in 5th period of first group, isn't it? So therefore principal quantum number value is nothing but period number is nothing but 5. It has ns1 configuration, valence cell configuration ns1. It has 1 electron in the s orbital, isn't it? Therefore L value is about 0 for s orbital. If L is 0, M also about 0. Then when you have only 1 electron in an orbital, probably that will be having clockwise spinning, isn't it? So that the s value is about plus of. So the answer is 500 plus of. So look at the options. 500 plus of. So option C is the right answer. Okay, right. Now question number 22. According to Bohr's atomic theory, which of the following transition will give least energy? Okay, you are given different transitions. So among these 4, which one will give least energy? So that is what you have to find out. Okay, right. Now we know very well that the energy difference is directly proportional to this one, isn't it? That is 1 by n squared minus 1 by n2 squared. That is energy difference delta E is directly proportional to 1 by n1 squared minus 1 by n2 squared, whereas here n2 is greater than n1, which means n2 is the higher cell, n1 is the lower cell. Okay, so now let us calculate energy transition for 2 cases. Electron from 6th cell to 5th cell. Electron transfers from 6th cell to 5th cell. Okay, right. The delta is directly proportional to 1 by 5 squared minus 1 by 6 squared. So that I am getting 1 by 25 minus 1 by 36. 36 minus 25 divided by the product of 25 and 36, about 900. Numerator 11. 11 by 900, 0.012. Okay. So for the transition of electron from 6th cell to 5th cell, that energy, change in energy will be proportional to 0.012, isn't it? Similarly for the next one, that is 5th cell to 3rd cell electron transition, delta E is directly proportional to a value 0.071, isn't it? Now just compare these two values. Which one is the least one? The first one. Okay, so that among the given 4 options, the transition of electron from 6th cell to 5th cell will be having energy about 0.012. That is the least one. Okay, so the answer is n equal to 6 to n equal to 5. Okay, right. Look at the options. N equal to 6 to n equal to 5. So option C is the right answer. Okay, right. Now question number 23. The total number of orbitals in the 4th energy level is equal to what? Okay, so you have to find out total number of orbitals in the 4th energy level, n equal to 4, isn't it? Whereas you know that in the 4th energy level we have all the 4 subcells, 4s subcell, 4p, 4d and 4f. So 4f subcell has only one orientation, 4p subcell has 3 orientations, isn't it? 4px, py, pz. Likewise 4d with 5 orientation, 4f with 7 orientation. So that the total number of orbitals is nothing but the sum of these numbers, it is about 16. So therefore the total number of orbitals which are present in 4th subcell is about 16. Okay, so 16 is the right answer. Okay. Number 24. The energies E1, E2 are of 2 radiations are about 25 electron volt and 50 electron volt respectively. Energy of two radiuses are given. One is 25 electron volt, another one is 50 electron volt respectively. Now what is the relation between lambda 1 and lambda 2? You have to find out relation between the wavelength of the two radiations. Right. So now this can be solved based on Planck's quantum equation. Okay, you know Planck's quantum equation is E equal to h nu, isn't it? That is hc by lambda formula. E equal to hc by lambda formula. Okay, so energy of first radiation, let us have hc divided by lambda 1, which is equal to 25 electron volt. Similarly, energy of second radiation, hc divided by lambda 2, which is equal to 50 electron volt. Okay, now I am going to take ratio between these two. Hc divided by lambda 1 whole divided by hc divided by lambda 2 equal to 25 by 50, isn't it? So I cancel hc in both numerator and denominator, and I interchange. Lambda 2 goes up, lambda 1 comes down, isn't it? And I cancel the right side also, 25 by 50, so 1 by 2. After cross multiplication, I will be getting lambda 1 is equal to twice lambda 2. Okay, so that the wavelength relation is wavelength of first radiation will be equal to twice the time of second wavelength. Wavelength of first radiation lambda 1 is equal to twice the time of wavelength of second radiation, that is twice lambda 2. So that the answer is option B, lambda 1 equal to twice lambda 2. Question number 25. If n is equal to 6, what is the correct sequence of filling of electrons in the given orbitals? Okay, so you are given ns orbital, n minus 2 f orbital, n minus 1 d orbital, and np orbital. We have to write exact correct sequence of filling electrons in these orbitals. Okay, right. So this can be done based on n plus L rule, sum of principal quantum number and azimuthal quantum number rule. Okay, n value 6, so that ns orbital 6s, np 6p, n minus 1d orbital, so it may be 5d orbital, n minus 2f in the sense it is 4f orbital. So you have calculated n plus L values for all these 4 different orbitals. Okay, 6s is about 6, similarly 6p, 5d and 4f, they are having equal n plus L value about 7. Okay, so here you have to remember the rule. If n plus L values are equal, the electron enters into the orbital which has lowest n value, isn't it? So first the electron enters into ns orbital which has lower n plus L value. Then after that, among the 6p, 5d and 4f orbital, so 4 of orbital has lowest n value. Okay, so after 6s the electron enters to 4f orbital, isn't it? Then after that 5d orbital, then it is 6p orbital. So that the correct sequence will be first ns orbital, the next 4f orbital, that is n minus 2f orbital, then after that 5d orbital, n minus 1d orbital, then finally np orbital. This is the correct sequence how the electrons are filled. Okay, ns, n minus 2f, n minus 1d. So look at the options. ns, n minus 2f, n minus 1d, ns, n minus 2f, n minus 1d, np. I think option A is the right one, isn't it? ns orbital, n minus 2f orbital, n minus 1 d orbital, then finally you have np orbital. Okay, so look at the answer. Okay, right. Next question number 26. A ball which has weight about 0.6 kilogram moving with a velocity 100 meter per second. Now what will be the wavelength of that ball? Okay, right. Now this question can be answered based on de Broglie relation. So you have to use de Broglie equation for finding out answer for this question. Okay, right. So de Broglie equation, lambda equal to h divided by mv, isn't it? H is nothing but Planck's constant, 6.626 into 10 to the power minus 34 kilogram meter square per second, and mass of the ball is given 0.66 kilogram into velocity. The velocity of ball is about 100 meter per second, isn't it? Okay, right. Now substitute all the values in the de Broglie equation. Now 6.6 and 0.66 gets cancelled. You get about 10 times. Then this is nothing but 10 power 2. When it goes up 10 power minus 2, so that 10 power minus 36. 10 into 10 power minus 36 is nothing but 1 into 10 power minus 35 meter. Okay, so the wavelength of the ball is 1 into 10 power minus 35 meter. Okay, so now look at the options. 1 into 10 power minus 35 meter. Okay, so option C is the right answer. Okay, right. Now question number 27. So which of the following has argon 3d6 electronic configuration? So you are given four different ions. Among that four different ions, one is having an electronic configuration which is equal to argon 3d6. That you have to find it out. That one you have to find it out. Okay, right. Now, so look at this. So you have to find out which one is having argon 3d6 configuration. Okay, so nickel 3 plus ion is given. Nickel atomic number 28. So that it has argon 3d8 4s2 configuration. So nickel 3 plus ion has argon 3d7. Then the next one, manganese 3 plus, atomic number 25, argon 3d5 4s2, manganese 3 plus in the sense argon 3d4 configuration. Then Fe 3 plus, Fe configuration argon 3d6 4s2. So Fe 3 plus, argon 3d5. Cobalt atomic number 27, so that it has the configuration argon 3d7 4s2. So cobalt 3 plus with argon 3d6 configuration. Now the last one, cobalt 3 plus ion is having the electronic configuration of argon 3d6. Okay, so that is the answer. The answer is the last option, cobalt 3 plus ion, which has argon 3d6 configuration. Okay, right. Now the question number 28. What is the maximum number of electrons in a subcell? So what is the formula to calculate maximum number of electrons present in a subcell? Okay, so the formula is 2 into 2L plus 1. Actually the formula is what? 2 into 2L plus 1, and the 2L plus 1 is multiplied by the 2, so that you are getting 4L plus 2. So this is the formula to calculate maximum number of electron present in a subcell. Okay, so 4L plus 2. So look at the option D is the right one. Okay, right. Now question number 24. Which one of the following quantum numbers is not possible? So you are given four different quantum numbers. Among that four option, one is practically not possible at all. Okay, right. The answer is actually option B. So directly we go for the answer. Answer is option B, because here principal quantum number is given about 3. Azimuthal quantum number L value is about 2. If L value is 2, M value is supposed to be minus 2 to plus 2 including 0, isn't it? Whereas here for L is equal to 2, M value is given as minus 3, but practically it is not possible. Okay, so that option B is the right answer for this question. Okay, right. Now question number 30. If delta x equal to delta p, that is uncertainty in position is equal to uncertainty in momentum, then what will be the delta v? In the question it is given delta x is equal to delta p, that is delta x is equal to m into delta v, isn't it? Then you know very well, this is nothing but Heisenberg's uncertainty principle expression, delta x into m delta v equal to h by 4 pi, isn't it? So in the place of delta x I am going to substitute this one, m delta v. So that this is nothing but m square into delta v the whole square is equal to h by 4 pi. I keep delta v square alone on left side. So m square goes to the right denominator, isn't it? So delta v the whole square equal to h divided by 4m square pi. Now you want delta v, so you have to take square root on right side. So therefore delta v equal to 1 by 2m into square root of h divided by pi. Okay, so that is the answer. Delta v equal to 1 by 2m square root of h divided by pi. Okay, so look at the options. So option C is the right one. Okay, so 1 by 2m square root of h by pi. Okay, right. So next question number 31. Question number 31. For an electron, delta P equal to 1 into 10 power minus 18 gram centimeter per second. Okay, so what is delta V? What is delta V? So for electron, uncertainty in momentum is given and they are asking delta V, uncertainty in velocity. So this can be answered based on Heisenberg's uncertainty principle, isn't it? So delta P is given 1 into 10 power minus 18 grams centimeter per second. They're asking delta V, isn't it? So now you are supposed to use this formula. Delta P is nothing but m into delta V. So after rearrangement, I get delta V equal to delta P divided by m. Okay. Whereas denominator m is nothing but mass of electron, isn't it? Right. Delta P, I substitute it here. 1 into 10 power minus 18 gram centimeter per second. In the denominator, mass of electron, but mass of electron you are supposed to substitute in gram, because delta P is given with a unit gram, so that the mass of electron also should be in the same unit. Okay, mass of electron 9.1 into 10 power minus 28 gram. 9.1 into 10 power minus 31 kilogram. In gram it is about 9.1 into 10 power minus 28. Okay, right. Now, so when this goes up, so it becomes 10 power 10, 10 power plus 28 minus 18 is nothing but 10 power 10. 1 divided by 9.1 is nothing but 0.109. Right, I write in a single decimal, so that delta V is equal to 1.09 into 10 power 9 centimeter per second. Centimeter per second, that is the delta V value. Okay, right. Now let us look at the options. 1 into 10 power 9 centimeter per second. 1 into, so look at the answer. 1 into 0.9. 1 into 10 power 9 centimeter per second. This is the right answer. 1 into 10 power 9 centimeter per second. Okay, right. The last question number 32. Splitting of spectral line in an electric field is called as. You know, the spectral lines which are produced by the atoms can be further splitted into simple lines, what we call it as fine spectrum, when the atoms are placed either in electric field or magnetic field. So this kind of splitting of spectral line into fine spectrum in presence of magnetic field is what we call it as Zeeman effect. If the same thing happens in presence of electric field, then that is called as Stark effect. Okay, right. Now the question is splitting of spectral line into simple line in presence of electric field, isn't it? So that phenomena will be called as Stark effect. So this is the answer for this question. Okay, right. Thank you.